An acoustic Doppler current profiler, or ADCP, is an instrument used to measure water current velocity over a depth range. It relies on the Doppler effect of sound waves to determine the speed and direction of currents at various depths. This is illustrated by sonar waves expanding outwards, with the frequency changing as they interact with moving water. ADCPs are important in oceanography, hydrology, and engineering for monitoring water currents. The Doppler effect explains how sound waves change frequency when there is relative motion between the source and observer. Imagine a car horn as it approaches and passes a stationary person. As the car approaches, the sound waves are compressed, creating a higher frequency pitch. After the car passes, the waves stretch out, resulting in a lower frequency pitch. ADCPs apply this Doppler principle underwater. They emit sound pulses that reflect off moving water particles. By analyzing the frequency shift in the returning echoes, ADCPs can calculate water current velocities. An ADCP emits short pulses of sound at a specific frequency. These sound pulses travel through the water column. The sound pulses bounce off small particles suspended in the water, such as sediment and plankton. The ADCP then listens for the returning echoes, which carry information about water movement. ADCPs calculate water current velocity by measuring the frequency shift between the emitted sound pulse and the returning echo. This is based on the Doppler effect in acoustics. A sound wave is emitted from the ADCP and reflects off particles in the water. The frequency of the returning echo differs from the original frequency due to the motion of the water current. The magnitude of this frequency shift is directly proportional to the velocity of the water current along the path of the sound beam. The relationship is given by this formula, where delta F is the frequency shift, V is the current velocity, F0 is the emitted frequency, and C is the speed of sound in water. To determine the full three-dimensional velocity vector, ADCPs use multiple beams pointing in different directions. Each beam provides velocity along its path, allowing calculation of the complete current vector. ADCPs divide the water column into discrete depth cells, called bins. This allows the instrument to measure current velocities at different depths simultaneously. The water column is divided into horizontal layers, each representing a specific depth range. These bins are typically 1 to 10 meters thick, depending on the ADCP configuration. The ADCP emits sonar pulses that travel outward in all directions. As these pulses propagate through the water, they encounter particles and plankton that reflect the sound back to the instrument. The returning echoes from each depth bin are processed separately. The Doppler shift in frequency for each bin's echoes provides the velocity measurement for that specific depth layer. By analyzing the echoes from all bins, the ADCP creates a complete profile of current velocity as a function of depth. This vertical profile shows how currents vary throughout the water column. ADCPs are deployed in two main ways, moored and vessel-mounted. Each method has different advantages and is used for specific measurement needs. Moored ADCPs are fixed in place, typically anchored to the seafloor. They measure currents at a single location continuously over time, providing detailed temporal data about how currents change throughout the day or season. Vessel-mounted ADCPs are attached to the hull of a research vessel or boat. As the boat moves through the water, the ADCP measures currents across a wider area, providing spatial coverage and mapping of current patterns over larger regions. Moored ADCPs excel at continuous monitoring with high temporal resolution and are cost-effective for long-term studies, but they only cover a single location and can be affected by biofouling. Vessel-mounted ADCPs provide excellent spatial coverage and flexibility, but they have higher costs and depend on vessel availability. For vessel-mounted ADCPs, bottom tracking is crucial. It uses sonar signals to measure the distance to the seafloor, which helps correct for the vessel's own movement through the water. This ensures the current measurements are accurate relative to the bottom. ADCP data serves numerous important applications across environmental monitoring and engineering. Let's explore some key real-world uses. One primary application is measuring river discharge for water resource management. ADCPs help track water flow rates in rivers, which is crucial for flood control, irrigation planning, and managing water supplies. ADCPs are essential for monitoring ocean currents, supporting navigation safety and climate studies. They provide data on current patterns that affect shipping routes and help researchers understand climate change impacts on marine environments. In coastal areas, ADCPs help study sediment transport, which is vital for understanding erosion, beach nourishment, and environmental protection. The data reveals how currents move sand and sediment along coastlines. ADCPs support offshore engineering projects by providing current data needed for designing underwater structures. This information ensures structures like oil platforms and pipelines are built to withstand local current conditions. Finally, ADCP data is used to validate hydrodynamic models, which are computer simulations of water flow. Real-world measurements from ADCPs help ensure these models accurately predict currents for various applications. ADCP measurements have several limitations that researchers must consider. One major limitation is signal attenuation in highly turbid water, where suspended particles can weaken the acoustic signals. Another limitation is interference from environmental noise, such as bubbles, marine life, or other acoustic sources, which can distort the Doppler frequency measurements. ADCPs assume uniform distribution of suspended particles in the water column. If particles are concentrated in certain areas, this can lead to inaccurate velocity measurements. Finally, ADCPs require careful calibration to account for instrument characteristics and thorough data processing to filter out errors and ensure measurement accuracy. Despite these limitations, ADCPs remain a powerful tool for understanding water currents and ocean dynamics, providing valuable data for scientific research and practical applications.